Hey everybody, this video lesson is brought to you from my back deck on a beautiful sunny afternoon. These are the introductory notes for Unit 11 in Solution Chemistry. It says Unit 10, but it's really Unit 11. This unit is going to consist of 3 weeks, 3 different labs, and some stoichiometry. We got definitely some math-heavy concepts, but this first video lesson is all vocabulary terms, which is why I'm doing it in a video lesson, because I can get through it quicker, and we can get on to the math and calculations much sooner. When we first started in chemistry back in September, I actually put this very picture up on the board. I talked about how we are going to be studying matter. Chemistry is the study of matter and energy. We talked about energy last chapter. Not all of it, but a lot of energy. In this chapter, we're going to talk about matter. Now, we really focused a lot on the left side here, the pure substances, elements, and compounds. Chapters 1 through 9 in gas laws discuss elements and compounds. Today, we're going to discuss the other half of matter, and that is the mixtures. Mixtures can be divided into 2 concepts, heterogeneous mixtures and homogeneous mixtures. Now, in fact, we talked about heterogeneous and homogeneous way back in September as well. But a heterogeneous mixture is an uneven mixture. Basically, if you can tell the parts of the mixture apart from one another, it's a heterogeneous mixture. A homogeneous mixture, on the other hand, is what we call a nice even mixture. An even mixture is one where you can't tell the parts that are mixed together apart from one another. Think pop or air that you're breathing. Air is a mixture of many different types of gases, but you can't pick one gas apart from the rest. By any physical properties, they're all colorless, they're all gas state, they're all pretty much the same, but they're not exactly the same. They're chemically different. And you might be wondering, why do I care about these concepts of heterogeneous mixture and homogeneous mixture? And the point is this: all homogeneous mixtures are solutions, which is the basis of this entire chapter. This table is something you're going to want to be familiar with, because there's going to be at least one question on the test about this little table. You can split up mixtures into 3 different types. Now, we just talked about 2 different types of mixtures, heterogeneous and homogeneous, but in fact, heterogeneous can be broken down into 2 different types. Mixtures are differentiated by particle size. Starting with the smallest and increasing in particle size, we begin with the solution, which has the smallest particle size. It's a homogeneous mixture. One thing that you can do to see and test if it's a heterogeneous or homogeneous mixture is, can it be filtered out? If the answer is no, if you can't filter out the substances from one another, it's probably a solution. An example being Kool-Aid, pop, sports drink. The next type of mixture is a little bit bigger particle size. It's medium particle size, and it's considered a heterogeneous mixture. Now, it also can't be filtered out because the particles are so small, but there are some aspects about it that make it a heterogeneous mixture. Namely, it looks a little cloudy. It's like we can kind of see through it, but it's not exactly completely see-through. If it looks a little cloudy, it's colloid. Milk is in fact colloid. Finally, suspension. Now, suspensions have the largest particle sizes, and this is definitely a heterogeneous mixture, and these particles can be filtered out. Think pulpy orange juice. So if you can differentiate a substance based on particle size, you can tell me whether or not it's a suspension, colloid, or solution. After this slide, you're pretty much not going to talk about colloids or suspensions for the rest of the chapter. We're going to focus solely on solutions, or the smallest type, the homogeneous mixture, the solution. Now we're going to begin the vocabulary section of this PowerPoint, and we've had some vocabulary words already, but these ones pertain specifically to solutions. Solutions are made up of 2 parts, the solvent and the solute. The solvent is what does the dissolving. Typically it's water. Water is known as universal solvent because it can pretty much dissolve anything, at least in a little bit. We say some things don't dissolve in water, like oil doesn't dissolve in water, but what we don't tell you is that it dissolves just a little bit. The solvent is defined as the greater amount in a solution. The solute, on the other hand, is a substance that gets dissolved. Now, the solute can take on any form. It could be a solid, liquid, or gas that dissolves. But the point is, if it gets dissolved in a solvent, it is the solute. It is the lesser amount in the solution. Inevitably, someone's going to ask me, what happens if you have exactly 50% of one thing and 50% another? Like, say, for example, 50% water and 50% alcohol, rubbing alcohol, for example. Which one's a solute and which one's a solute? And I would say that neither of them are solute or solvent if you have 50%. But as soon as you have 51% of one and 49% of the other, the 51% is the solvent and the 50% is the solute. Now, you definitely don't have to know or memorize anything off of this table, but it's just basically there to show you that the solutions can come in any type. We focus a lot on this these liquid solutions, these solids dissolved in liquids, or these liquids dissolved in liquids like salt water, vinegar, or even carbonated drinks. Some of you are probably drinking one right now. But what you probably don't think about are all different types of solutions. If you dissolve a gas in a gas, for example, like the air you're breathing, that's considered a solution. If you dissolve liquid in a gas, any humid air, right now there's some liquid vapor, water vapor dissolved into the air. It is known as humidity. Going down to the solids down here, down on the bottom, you've got liquids dissolved in solids, like amalgam, dental amalgam. Mercury is a metal, and silver is a metal. Mercury is a liquid, silver is a solid. Another one is a solid. These solid solutions typically are what we call metal alloys. Not everything dissolves. That's a key concept, and one of the key concepts of this early stage of this chapter. Definitely have a question about this on the test. Not everything dissolves. Sometimes you have things that dissolve, and sometimes they don't dissolve. In order for two things to dissolve, they have to have the similar or same polarities. Ionic and polar covalent are pretty much considered to be the same, and ionic is just a very, very, very polar substance. And so sodium chloride, for example, which is ionic, can dissolve in H2O, which is a liquid, which is very polar covalent. Basically, if the substance has a pole, or if it's an ion dissolving into something that's polar, it will dissolve. Now, something that will not dissolve in polar is something that's nonpolar. Nonpolar dissolves in nonpolar, but they don't mix. The example of nonpolar substances like oil, plastic, gasoline, these substances won't dissolve in one another. Classic example of when you try and mix two things that dissolve, or you're trying to dissolve, is oil and water. Oil and water do not mix. Oil sits on top of water. They don't mix. They form this nice layer of oil and water, and you can basically pour two liquids on one another, and they automatically separate into oil and water. Which brings me to one of my favorite chemistry jokes. What type of bear dissolves in water? That's right, the polar bear. The term solubility refers to the ability of a solute to dissolve in a solvent. So if we say something is soluble, we means it will dissolve. If we say it's insoluble, it will not. For example, soluble is something ionic, like NaCl in water again. If you take NaCl and put it into a cup of H2O, it will dissolve. Oil will not dissolve. Now, when you're talking about things that are specifically liquids dissolving in other liquids, we use some other terms called miscible and immiscible. Miscible means liquid dissolve in a liquid. Like, for example, before I told you, water will dissolve in rubbing alcohol, for example. Those two liquids are considered to be miscible. Immiscible liquids are like oil and water. And the reason they don't dissolve is because oil is nonpolar and water is polar. Now, how does the solute and solvent actually interact with one another? Simply getting together doesn't necessarily mean that they will dissolve, but in fact, the particles have to come in contact with one another. And when they come in contact, the solute and solvent interact with the polar ends and the nonpolar ends in a way that results in dissolving. The point is, some of you never really thought about when something dissolves, like salt dissolves in water or sugar dissolves in water. But in fact, you can dissolve something by getting it to come in contact with something else. And the more contact you can get between the solute and solvent, the faster something dissolves, which brings us to our next slide. How fast you can get something to dissolve is called the dissolution rate, or rate of dissolution, to dissolve. Three factors that affect the rate of dissolution, or dissolving, are increasing the surface area, agitation, or temperature. Increasing the surface area by crushing up or making the particles smaller allows for more interactions between the solute and the solvent. The same with agitation. You get more interactions between the solute and solvent. You shake, swirl, or stir, and you get more solute bumping into more solvent. So if you can crush and stir, that's a big advantage over something that's not stirred and not crushed up. Finally, increase the temperature. Increase the temperature of the solvent allows for the solvent particles to move faster. And again, all of these increase or get the solute to touch the solvent more often. Now, if you are taking notes right now, I would star this because this is an excellent test question. Which brings us to our last slide of the day. Saturation. The concept of saturation is how much will something dissolve in the solvent before it reaches its maximum. The maximum amount of solute that will dissolve in a solvent is known as a saturated solution, meaning it can't take another atom more. And if you do put more salt, for example, into water and it's at a saturated point, the salt will not dissolve and the salt will just simply trickle down to the bottom of the beaker, leaving you with just wet salt in the bottom. Unsaturated is the term we use to describe anything less than the maximum amount. So if you have pure water and you put like just a spoonful of sugar in and stir it up and it all dissolves, chances are it's unsaturated. It means it doesn't have the max yet. So you put in another scoop, stir it up, and if it dissolves, it's still unsaturated. But as soon as you put in just the right amount where it can't take another bit more, it becomes saturated. Now, supersaturated is a concept that, if you're lucky, I'll show you in class. But it's basically a situation or special case when a solute is dissolved into a solution at high temperatures. When the stuff dissolves at high temperatures, you can dissolve more at a high temperature than you can at a low temperature. And then you allow it to cool down undisturbed, and then something really interesting happens. And when you toss in or agitate the supersaturated solution, a crystal comes out of solution as if just out of nowhere. It's pretty cool, actually. That takes care of these introductory notes for this first part of Chapter 11. Thanks for listening.